the history of electromagnetic theory. The story begins with the works of Michael Faraday and Andrew Mary Ampere in the early of 19th century. Faraday's experiment with magnets and electric current led to the formulation of Faraday's law of electromagnetic induction. Ampere's work, on the other hand, focused on the interaction between electric currents and magnetic fields. In the mid-19th century, James Clerk Maxwell synthesized these findings and developed a set of equations that describe the behavior of electric and magnetic fields. Maxwell's equations complete in the 1890s, and these are a set of 4 fundamental equations. So, the first is Gauss' law for electricity, Gauss' law for magnetism, Faraday's law of electromagnetic induction, Ampere's law with Maxwell's addition. However, Maxwell's equations were not complete. They successfully described the relationship between electric and magnetic fields, but lacked a term to account for changing electric fields in a way that was consistent with the other equations. Let us move on to the introduction of displacement current. To address this gap, Maxwell introduced the concept of displacement current in the 1861. The idea was to incorporate a term that accounts for changing electric fields, particularly in regions where there is no actual flow of charge, such as in capacitors. Maxwell realized that a changing electric field could induce a magnetic field, similar to the way a current does. To represent this, he introduced the displacement current term symbolized by epsilon naught times to the delta E over delta T, where epsilon naught is the permittivity of free space and delta E over delta T represents the rate of change of the electric field with respect to the time. The rate of change of the electric displacement field is known as the displacement current. It is calculated in the same way as electric current density is calculated. Maxwell's equation includes a term called displacement current. It was created to bring the Ampere circuit law into line with logic. So, the Ampere amp is the SI unit for the displacement current. This dimension can be measured in the length units, which can be maximum, minimum, or equivalent to the actual distance travelled from the start to finish. Displacement current is an electric current created by the time varying electric field rather than by moving charges. So, what is the characteristic of the displacement? Current displacement current is another type of current apart from conduction current. As with conduction current, it does not appear from the actual movement of electric charge. It is a vector quantity and it is vital for electromagnetic wave propagation. So, Maxwell's complete equations. With the inclusion of displacement current, Maxwell's equations took their final form, which are for the Gauss law for electricity, Gauss law for magnetism, Faraday's law of electromagnetic induction, and Ampere's law with Maxwell's additions. The inclusion of displacement current complete the set of equations and successfully unified electricity and magnetism, predicting the existence of electromagnetic waves. Let us move on to the significance of displacement current. The displacement current plays a crucial role in understanding the behavior of electric field in the region where charges are not physically moving but where electric fields are changing over time, such as in capacitors and during the propagation of electromagnetic waves. The validation of Maxwell's equation with the successful detection of electromagnetic waves of Heinrich Hertz in 1888 provides experimental evidence for the existence of displacement current and laid the groundwork for the development of wireless communication technologies. The concept continues to be a fundamental aspect of modern electromagnetism and plays a key role in fields such as telecommunications, electronics, and electromagnetic wave propagation.
Okay, next for the Maxwell equation. For the derivation, we know that from the continuity current equation, the divergence of J is equal to negative D over dt rho V. And then we can change the vector of J to the curl of H. and we will get the equation as the divergence of curl H is equal to negative D over dt divergence of D. And then we can solve the equation by zeros to the left hand side by using the vector identity, and we will get the equation of the Maxwell equation is that the curl of H is equal to J plus JD. Next is the key changes for the Maxwell equation. We know that the key concept for the Maxwell equation is the displacement current itself, which epsilon naught dE over dt. This term is for the changing electric field in a region even in the absence of actual electric charges. Displacement current is important, for example, involving changing electric field in charging and discharging of capacitor. For the capacitor, during charging and discharging of a capacitor, time-varying electric field produced or exists between the capacitor plates. During charging of capacitor, the voltage is applied across the capacitor. The electric field between plates increases. As electric field changes, which increases, the displacement current contributes to the magnetic field around changing circuit, which affects the behavior of the magnetic field in the region. Then for the discharging of capacitor, when capacitor discharge, the stored electric field between the plate decreases over the time. The changing electric field leads to the displacement current influencing magnetic field in discharging circuit.
Okay, now we move to the next part, which is the relation of Maxwell's equation to the concept of displacement current. First of all, we should know Maxwell-Ampere law. The progress of the theory of displacement current can be traced back to a famous physicist named James Clerk Maxwell. Maxwell is well known for Maxwell's equation. The combination of four equations demonstrates the fundamental of electricity and magnetism. For displacement current, we will be focusing on one of these equations known as the Maxwell-Ampere law. Fun fact, before Maxwell, Andrea Mary Ampere had developed the famous equation known as Ampere law. This law is related the magnetic field surrounding a closed loop to the conduction current traveling through that loop multiplied by a constant known as the permeability of free space. So now we will explain about the Maxwell's equation. Maxwell's equation is defined as the displacement current which has the same unit as the electric current. The Maxwell field equation is represented as curl cross H equal to J plus JD, where H is related to the magnetic field B, as B is equal to mu H. Mu is the permeability of the material between the plates. J is the conducting current density. Meanwhile, JD is the displacement current density. For a perfect dielectric, which is a special case, J will be equal to 0. Hence, curl cross H is equal to JD, which is the equation for a perfect dielectric. Okay, now we move to the next part, which is the displacement current using Maxwell's equation. For the previous part, I have shown the history of the Maxwell's equation. Now we want to learn more about the Maxwell equation by displacement current. Maxwell adjusted the main relation of Ampere's second law with an additional term. This made the relationship complete and wholesome, with both static and time-varying parts present to play their part. The derived term that's shown in the next part is known as the displacement current density formula. This comes in use when time-varying fields are required, such as a constant displacement vector. Okay, to the last part for the Maxwell equation with displacement current. For the last part, we will derive the displacement current using Maxwell's equation. Maxwell adjusted the main relation of Ampere's second law with an additional term. So we derive the equation by using the Maxwell to get the displacement current. At first, we take the magnetic field intensity without the magnetism, B equal to mu H, and then addition of an additional term JD in the above equation. So the equation will become curl cross H equal to J plus JD. And then we perform the divergence action. Curl dot in bracket curl cross H close bracket equal to 0 and equal to curl dot J plus curl dot JD. To define the JD term, we use the curl dot JD equal to negative curl dot J, also equal to dPV over dt. By using a Gauss law, curl dot D equal to P, where D is the displacement vector and P is the charge density. And the equation will become dPV over dt equal to d over dt in bracket curl dot D close bracket equal to curl dot dt dd over dt. Also, curl dot jd is equal to curl dot dd over dt. Therefore, the final equation will become jd equal to curl dot dd over dt. This derived term is known as the displacement current density formula. This comes in use when time-varying fields are required, especially for a constant displacement vector.
For the last part, I'll be talking about real-world application of the concept displacement current, which is electromagnetic relay. First, let's start by understanding what electromagnetic relay are and why they are crucial in the industrial automation. Electromagnetic relay are electrical switches that uses electromagnetism to control the flow of electricity in a circuit. They are essential in industrial automation system for controlling machinery, process, and other critical components. Before we delve into how displacement current comes into play, let's review the key component of an electromagnetic relay. A relay typically consists of a coil of wire wound around an iron core, an armature movable switch contact, and a set of fixed contact. These components work together to control the flow of electricity throughout the relay. Now, let's explore how an electromagnetic relay operates. When a voltage is applied across the relay coil, an electrical field is established within the coil. According to Maxwell's equation, this changing electrical field induces a magnetic field around the coil, generating the displacement current within the coil. Now, let's talk about why is displacement current important in the operation of electromagnetic relay. Displacement current is crucial for establishing and maintaining the magnetic field around the coil. This magnetic field is what attracts the armature towards the fixed contact, closing the circuit and allowing the current to flow through the relay's contact. Now, let's consider an application example to illustrate the importance of electromagnetic relay in industrial automation. In manufacturing plants, electromagnetic relays are used to control various processes and machinery such as conveyor belt, robotic arm, and even assembly lines. Displacement current ensures the reliability of switching these functions, contributing to the efficiency and productivity of industrial operations. That's all from us. Thank you very much.